Welcome to this morning session in Brazil and the US, afternoon in Europe, and late night in Japan and in India, I guess. Welcome everybody. Our first talk this morning is a review talk by Alfredo Guevara from Harvard about amplitudes and GR.
Okay, thank you very much. Let me just thank the organizers, of course, for putting together such a wonderful and comprehensive program. So I got the very hard mission of providing a review on this topic, which is kind of interdisciplinary. So currently has people working together from high energy physics, people from pure relativity. So there's a lot going on. So I thought, of course, I'm going to start from just the previous time such a topic was reviewed in this conference, which apparently was never. So because it's the first time, I'm going to start with just basic ideas. Hopefully, will be some kind of pedagogical introduction to the topic, and hopefully, by the next 40 minutes, we will all make it to the state of the art computations. So, of course, let me just thank my collaborators and my friends who I've been having the pleasure to discuss these topics, and I've learned so much from them. And in particular, I would like to say that, as I said, there's a lot of people working on this, and please excuse me if I forget one or two references. I would probably not be exhaustive in terms of references. Okay, so let me just start by providing a general picture. So we know that general relativity is one of the prime examples of an effective field theory. This means that it describes, to the best of our knowledge, the low energy regime of putative quantum gravity theory. And as such, it has beautifully succeeded over the last 100 or so years in making very precise predictions at the scales we can currently measure with our technology. Okay, but as we know, as technology progresses, so does the precision of our detectors. And even though quantum measurements are still out of reach for our detectors, we can now test GR to an unprecedented, to an exquisite precision, which is expected to increase over the years. So in a sense, we have been very lucky because the technology we have been developing for detecting gravitational phenomena have been keeping the pace with our current estimations derived from Einstein's equations. So as we know, as technology progresses, we're going to need more precise estimations. Okay, so this is just a general picture, but you can tell already that this brings up two major problems. And these problems have been around for, as I said, 100 years or so. The first one is actually, how do we solve Einstein equations for realistic, time-dependent dynamical processes that happen to occur very commonly? And the second is, what observables of GR should we focus all our machinery in computing? Okay, so what are the right observables we should be discussing? So I'll just leave you with these pictures, and you can tell what kind of observables we can derive from them. So let me be more precise. The first problem has to do with the fact that in graduate school, in order to devise exact solutions for general relativity, we usually assume very simplifying assumptions, such as high amount of symmetry. So we assume that there's some time-like Killing vector, there's some spherical symmetry, or there's some symmetry of the base manifold, or we look for BPS states and so on. And we arrive at these very nice and beautiful symmetrical solutions that we know and love, and they have very interesting properties. Some of them are integrable, they have very remarkable interpretations. Here you can tell from a textbook, this is from Elders and Kuhn in the 60s, that all these solutions have certain interpretations. A1 is, of course, the Schwarzschild metric, there's the symmetric, and so on. So all of these solutions are remarkable in a way or another, but however, they fall short when we want to describe more realistic scenarios. Okay, and such realistic scenarios that we deal with today can be, for example, the perturbation of a black hole background by something that's not symmetrical, or the actual merging of two black holes. Okay, so that's the first problem. What's the second problem? Well, the second problem is that the main observables. So what are the observables we need to compute? So the main observables, for instance, we compute in quantum field theory, are scattering amplitudes. And we know that scattering amplitudes have been very successful because we can measure cross sections, and they have driven so far our current success at large particle accelerators. So the cross section is something concrete that we can estimate. But we know infamously that such a framework cannot be applied to quantum gravity because of the presence of UV divergences. So we cannot get such predictions from quantizing a theory of gravity. Okay, so scattering amplitudes at face value seem not to be a good candidate for observable. So instead of doing that, in GR we consider a similarly unrelated set of observables. So we consider, for instance, the gravitational lensing. So basically, we examine pictures of our observations of electromagnetic radiation, so we can tell what's the polarization of the light that's coming to us. We can look at in gravitational wave astronomy, certain fluxes, time delays. All of these observables are encoded in the waveforms that people analyze. So there's a similarly unrelated set of such things. But there's a problem with that. And the problem is that these are, of course, happen to be very difficult to compute for realistic situations, such as I said, the merger and so on. And in the case of the gravitational wave merger, for instance, we need to rely on certain combination of analytic methods, so-called post-Newtonian theory. So the post-Newtonian theory basically is a perturbative approach to solve the two-body problem in general relativity. But because instance equations are highly nonlinear, post-Newtonian theory, this perturbative approach escalates very quickly and becomes increasingly hard to get a handle on. Okay, but if you do want to get a handle on, and you go and do post-Newtonian theory, something like this in the left-hand side is what you're going to find, tons of diagrams that you have to compute. And when you're computing them, you're solving instant equations. Usually, you're going to use a computer. This kind of reminds us, of course, of the complexity associated to computing Feynman diagrams and precision processes in the scattering of fundamental particles. So in both cases, we have to compute a huge number of diagrams, we have to perform integrations and so on. And it's not surprise, as I'm going to show now, that these two kinds of complexities are completely, they are very much related, okay? So the same kind of tools we use for computing these processes in quantum chromodynamics can be used for computing certain processes, but in a very particular and different way than the post-Newtonian theory. Okay, so that brings me to the goal of the talk. So I pretend to give you a flavor on how we can use scattering amplitudes in quantum field theory, scattering amplitudes in a theory coupled to gravity, to define first and second compute classical observables in general relativity. Okay, moreover, such observables are going to characterize dynamical scenarios such as black hole perturbations on, for instance, the two-way problem. So the nice thing about the observables we're going to construct is that they are free from UV divergences, since they are defined in a classical limit of the scattering amplitude. So what the classical limit means is basically we're going to consider low exchange momentum. And classically, we expect then to describe dynamics where, of course, the massive compact objects in general relativity, these gravitating objects are distanced certainly larger than their charging rates. Okay, this doesn't mean that we cannot prove certain strong gravitational effects, but for sure we're not going to prove inside the horizons. Okay, so in such a regime, we can fully trust GR as an effective field theory, and indeed we can compute observables to high accuracy in the Newton's constant. Okay, so that means we can do precision grading, and in particular we can consider the exact dependence on the velocity of these compact objects that, for instance, merge or are gonna accelerate because of radiation. So such a framework we will refer to as the post-Minkowskian theory, in contrast to the previously mentioned post-Newtonian theory. Okay, so the key words here are scattering amplitudes in quantum field theory. So the relevant scattering amplitudes can be computed using novel on-chip methods. Okay, what that means is that we're going to enforce the principles of unitarity and locality that are contained in this underlying quantum gravity theory. And by using such principles, we're going to bypass the evaluation of tons and tons of Feynman diagrams that you would usually have to put on the computer. And we know that such a powerful tool, which is Unitarianity, is completely invisible, or at least is not manifest when we are solving Einstein equations perturbatively, say in the post-Newtonian approach, taking as face value, there is no way we're implementing Unitarianity. So this is a novel tool in this context. So the kind of amplitudes we're going to deal with, they are usually in high energy physics, and they are basically graviton exchanges. And the key point, of course, that we're only going to consider on-shell quantities. So this effectively provides a new analytical window into perturbation theory in gravitational physics. Okay, so let me start by just from the very basic construct certain observables in gravitational physics, just from amplitudes. Okay, so to begin with, I'm going to be interested in observables that can be measured at far distances in asymptotically flat space-time. So that's the case for a gravitational wave that is emitted by certain process, dynamical process. So here, these arrows are basically word lines that are colliding, or there's some dynamics. You can throw some gravitational perturbations and so on. But at the very end of the day, what you're measuring is gravitational flux. That's the outcome of this process. So this device here is our detector. Okay, so we place it at non-infinity. And of course, the key starting point is the perturbative approach. So I'm gonna basically expand around the flat metric, but this perturbation doesn't need to be linearized perturbation. We can have all orders in the gravitational constant. Okay, so the radiated part of the metric that I'm gonna look at, of course, measured at new infinity, is usually computed from a source. So this effective source, as you can see here, basically contains all these dynamical processes, right? So it's not just matter, it contains gravitational back reaction. So there can be all kind of, this is usually called the pseudo-linear stress energy tensor of gravity and so on. There can be all kind of dynamics happening in this blob. But at the very end, you're going to have this effective source with compact support, and you're going to perform this Fourier transform. If you want to measure it at non-infinity, you can use some saddle point approximation. This is a textbook exercise. And you're gonna get to the result that basically the metric that you're observing at non-infinity is directly related to the stress energy tensor, or the source, in momentum space, where your momentum is pointing towards your observation direction. Okay, that's the key point. Okay, so but what's the problem? Okay, the metric itself is not an observable. Okay, it's a gauge-dependent quantity. So in order to encode gauge invariant information of the metric, which is the radiated data that we're measuring, we are going to consider certain components. So start by defining this null tetrad. So all these vectors, I'm going to expand them in metric in this null tetrad. All these vectors are null. The only non-trivial inner products are these two. So these are conjugates. Now, the way I think of this tetrad is as follows. So L here is pointing in certain direction in the celestial sphere. M plus and M minus are complex directions. Okay, so what they do is they parameterize the celestial sphere as a Riemann sphere. And because they are complex directions, they inherently have some ambiguity, which is a phase. Okay, so they transform in this phase, and this is a helicity transformation, so to say. So here L parameters certain directions, and M plus and M minus are just directions in this complex sphere in celestial sphere. So in order to extract certain components, for instance, if we are looking at the metric has helicity 2, or the gauge invariant definition of the metric is a helicity 2 quantity, which we call the Newman-Penrose scalar, or the Newman-Penrose amplitude, which is obtained from the Weil tensor as follows. So we project it with M, certain component which has helicity 1, and N, which is conjugate to the null vector L. Okay, so if our point of observation is at angles theta and phi, using our formula for the Weil tensor, because as I said, we computed the metric already at null infinity and it's given by this formula. using this formula and plugging this into the Weyl tensor, we are going to get to this point where basically the Newman-Penrose amplitude is related to the source, where the momentum of the source is evaluated in the direction of observation, which is this L vector. Okay, so that means, because L is a null vector, that we can think of L as being some momentum of a certain perturbation, in this case, a gravitational wave. And because M minus and M plus are orthogonal to L, and they are also null vectors, we can think of M's as being polarization vectors. Okay, so this is basically what I'm getting from this Newman-Penrose scalar defined in this way, is that I'm contracting this polarization vector associated to L or K with this source with momentum K. Okay, and K is pointing in my observation direction. So if I look at the LS formula, in quantum field theory, this is basically a classical limit of a scattering amplitude. Okay, so I'm contracting my source in certain components, and it's a gauge invariant quantity. Okay, so the scattering amplitude is obtained by considering a quantum field theory amplitude. Okay, so this is the invariant component of the Newman-Penrose amplitude, but we have to take this classical limit. Okay, so it's some quantum field theory amplitude where we emit a graviton and we take some classical limit. Okay, so interestingly, the derivation can be done in quantum electrodynamics. It's the same. Of course, it's a textbook exercise. But this funny thing where basically for certain spacetimes, which I just described, these are algebraically special, meaning that the Weyl tensor has certain properties which make it special. For certain spacetimes, the two computations are closely related, and in fact, one can perform the computation in QED and obtain the result in gravity. And such a relation is called the double coupling. Okay, so just to mention that this has no additional difficulty as compared to the electromagnetic case so far. So the question is you're asking right now is how do we actually take the classical limit? So we know that this amplitude is emission of a graviton, but we have to take the classical limit. So formally, in order to get a macroscopic observable, so a microscopic effect, you need to consider a coherent superposition of many gravitons to form this gravitational wave. Okay, and this has been done in different contexts by these authors. We will explain that in a second. But for now, let me just mention that in practice, we're going to take a single graviton and we're going to define this classical limit in a precise way, and that's going to give us the actual classical amplitude. Okay, the Newman-Penrose amplitude. So let me just give some examples of how this works. So the simplest case, just linearize gravity. So consider a massive body or consider many massive bodies. So these massive bodies, they are accelerating. It's a stress energy tensor. So just the matter part of the stress energy tensor is given by this formula. So they all have some initial momentum, P1, P2, P3. And I'm looking at momentum space. So I'm going to consider perturbations of momentum K. Okay. So this is a leading order in the energy of the perturbation. The stress energy tensor looks like this. So we're only gonna need such a leading order. And for instance, if we consider a single particle, so the simplest case, we can write, because there is no other particle, so conservation of momentum, the momentum tells you that the finite momentum is gonna be P1 plus K, where K is the momentum of the wave. And basically what you get from this equation is a delta function, because the denominators just subtract and you get this delta function here. And this is nothing but an on-shell condition. And in fact, you can very easily recognize this as 3-point amplitude of a massive scalar coupled to a graviton. Okay, so it's a unique 3-point amplitude. So these two computations are closely related. So one is a stress energy tensor of a single massive body, and the other one is a computation in quantum field theory. Okay. Now, what happens if we have more than one body? So we have two bodies, for instance. So in linearized gravity, the graviton is going to couple to either one or the other one, right? So we have sum of two terms, and this is the amplitude. Now, in quantum field theory, we recognize this expression immediately at the Weinberg subfactor. However, we know that the subfactor is not the full amplitude. So if I take the 5-point amplitude corresponding to this process of a graviton emission, I know that in the soft limit, I'm going to get this subfactor times some other hard piece. So this is the standard soft limit. But now you may ask, we know that in classical gravity, the amplitude is a subfactor. Then what happens with this hard piece when we take the classical limit? Okay, so that's very, it's a small puzzle. So what actually happens? No, what happens is that actually we're solving different scattering problems. So this amplitude is classical already in the soft limit, but the problems are different. In quantum field theory, we compute a transition probability for certain states for which the momenta is fixed at the past and the null, sorry, the past and the future infinity. Okay. Whereas in classical gravity, or in this initial value problem, the initial data is given by velocities and positions. So in this problem, in the classical problem, the momentum deflection is actually computed by integrating the equations of motion, and therefore it's not a variable. Okay, so these are different problems. They are both scattering. But we can take one problem to the other. It's very easy because we can translate using wave functions. So in quantum field theory, we can consider a wave function that describes a particle, a classical particle, moving into an asymptotic trajectory. Of course, now you might say there are no asymptotic trajectories because there's some long distance Coulomb drag, but let's ignore that Coulomb drag in linearized gravity. This already doesn't matter. So we can consider these three massive particles evolving in straight lines. Now, the wave function associated to that, because basically you're starting from certain positions V1 and V2, is shifted in this form. So you have these exponentials. And you have an envelope that its sole role is to project your scattering amplitude into certain classical momentum. So this is the envelope function. We consider it has some width L, but the width L is very small as compared to the observation distance. Okay, so we're going to look at it from far away. And basically, the envelope is not, it has no width for such purposes. And the other thing you have to consider is that the momentum transfer associated to such a particle, because it almost moves in a straight line, it deviates very small, it has a very small deviation because this is linearized gravity. So the momentum transfer is going to be far less than the mass. Okay. So when you consider such wave functions and you project your quantum field theory amplitude in such wave functions, you get this formula. Okay. So this is the classical amplitude. So now you can take the soft limit at both sides. Remember, this was a soft theorem. This was a soft factor, sorry. And this gave you the soft theorem. So this has to do with the four particle amplitude. And you get that in order for the two sides to be consistent, you need this formula. So this formula tells you the classical momentum deflection as a function of only the initial condition, this impact parameter, which is V1 minus V2, the difference of positions. And it reveals that the role of this four-point amplitude is nothing but to integrate the equations of motion. Okay. So you can tell, for instance, that already here, because it's a Fourier transform in Q, only the divergent part in Q is going to contribute. So that means that we can only take the small Q limit. It's enough to consider the small Q dependence on this amplitude. That's precisely what we assume to begin with. Okay. Sorry, there's some background noise, or is it Nathan? Okay, thanks. So this relation, you can convince yourself that is basically a relation between the scattering amplitude and some effective potential that controls these dynamics. Okay, so this is the usual Born approximation where we relate the potential to scattering amplitude. So the difference between this and that is that this equation is expressed in terms of observable quantities. In particular, this momentum deflection is basically the scattering angle from, the initial momentum to the final momentum is a scattering deflection. So it's an observable, it's a gauge invariant quantity. Whereas this is, of course, gauge invariant, and you need to assume some gauge and so on. But this is an observable in gravitational physics. And we just derive it from a scattering amplitude. So the previous formulae for the 5-point and 4-point amplitudes are the simplest cases for linearized gravity of something that we now call the Kosover-Maybe-O'Connell formulae, which link quantum field theory amplitudes to classical observables, okay, in the scattering problem. So these are both scattering processes. So we will now provide a complementary perspective on such a formula, okay, and that perspective is suitable for going to higher and higher orders, and at the same time we can relate that to the bounded orbit problem, which is actually, for instance, if you have elliptical orbits of one body with another, that's basically what you're looking at in the gravitational wave mirrors, in the black hole mirrors. So we want to understand what happens when these bodies don't scatter but keep orbiting each other. Okay, so of course I have not yet given a satisfactory explanation as to why these microscopic effects, such as scattering of a single quantum, a single graviton, lead to macroscopic observations in gravitational physics. Okay, so to the best of my knowledge, the simplest way to understand this is through the O'Connell approximation in quantum field theory, which has been developed long ago. Now, we consider, in order to introduce this O'Connell approximation, consider the 4-point S matrix of two massive particles. So here I have two different mass particles interacting through gravity. Now, we can take the low momentum transfer limit, which is basically forward scattering. Okay, so we assume in accordance with our previous assumptions that this momentum of the world line change is very, very, very little. So in this regime, the amplitude is dominated by these diagrams. That's something, that's just a fact, you can check. So because the momentum transfer is very little, so the momentum that flows from one line to the other, basically these propagators here, they are almost unchecked. Okay, so that means that basically this is a product of 4-point amplitudes, this ladder diagram. But if you look at it, of course, there is some loop integration running. So basically what you get is some kind of convolution between this amplitude and this other because of the loop integration. However, if you Fourier transform to certain position space, which is the impact parameter space, so let me define this chi as the Fourier transform of this 4-point amplitude. Okay. If you Fourier transform, then you undo this convolution of the loop integration, and you basically can factor all these ladders into a product of this quantity, which is a 4-point amplitude, okay, at 3 levels. So what you've just done is to resum all this loop expansion, all these ladders, in a factorized way into some exponential, okay, and the combinatorics just work out. So that means that all these microscopic processes, repeated one and over again, lead you to a macroscopic effect, which is the O'Connell phase, which is this kind that I just defined. So in particular, this O'Connell effect, the O'Connell phase is an observable quantity, and it can be used to construct the observables that we have just defined. For instance, if you take the derivative of the O'Connell phase with respect to B, remember of this formula, if you take the derivative with respect to impact parameter, you get the formula that I just presented 3 slides ago, called the Kosover-Maybe-O'Connell formula. Okay, so this is O'Connell phase is at the heart of this construction. Now, the exponential structure of this matrix just reflects that gravitons are just in coherent superposition. Okay, in particular, it shows that the classical information can be contained in loop diagrams. Okay, we have so far only considered factorizations into 3 amplitudes. That's equivalent to computation in linearized gravity. So this computation has been understood in many different ways. And basically it's just computing a probe particle in the background source by the other particle. Okay, but by now, I mean, a few years ago, we understand how to extend this O'Connell approximation to something that's called the sublinear O'Connell and so on, in which the phase contains information not only of a probe particle scattering in another background, but actually the full gravitational two-body problem, meaning these two bodies are of comparable masses. Okay, so it's not a probe limit anymore. And this iconal phase is computed by something that contains loop diagrams and so on. But these at the very end are classical results. Okay. So we have constructed this iconal phase. So how do we get observables from it? Well, basically, if you take this formula, which is the iconal approximation, this exponential that I told you, you can kind of interpret it as some path integral where you are fixing the initial and the final momentum. This is basically the scattering angle. So it's basically related to this momentum transfer. And you're integrating all possible trajectories basically by varying this impact parameter, which is the distance of the collision. So this shows you on the nose that this iconal phase is nothing but an effective action. So it's an action that you put into your path integral, but it's only the radial part. Okay, so it only depends on this radial direction. So in Hamilton-Jacobi theory, you compute your effective action, and because you have some time symmetry and angular symmetry, basically the only interesting part is this radial component, and I'm claiming now that this radial component is nothing but the scattering phase. Okay. So one thing to note is that the angular momentum part is related to the impact parameter by this formula. Okay. But now that we have this radial action from the iconal phase, we can very easily solve the bounded problem, because so far we have considered the unbounded problem in which the radial action is integrated from this R, which is the point of minimum distances in the scattering situation. If we go to the bounded problem, basically you have to integrate this radial action from the two extrema of the motion. Okay, so they are related somehow. The observables that you can compute in the unbounded case, basically from Hamilton-Jacobi theory, by differentiating this radial action, are the scattering angle, the classical scattering angle, and the Shapiro time delay, which is a very important constraint that you want to compute for purposes of causality. So you want to have a time delay, not a time advance. So this is a very important observable in the scattering problem. In the bounded case, you have periastron precession, meaning that some bounded orbit is going to be deflected for each cycle, and the period precession, which is kind of self-explanatory. So the claim now is that there is a relation between those two, given by this radial action, and this was found by Porto and Kelly, so I forgot to mention the reference. But basically, the relation is given by this analytic continuation. When you take the momentum of the incoming particle and take it to the imaginary axis, this takes the energy negative. And if you actually look at the iconal amplitude, you will find that it actually has poles for such momentum. And these poles, they were shown to be actually the spectrum, or at least a leading order in G. They correspond to certain atomic spectrum of this bounded problem. Okay, so this analytic continuation takes you from the scattering situation to the unbounded situation, sorry, to the bounded situation. Okay, so I hope by now I have convinced you that the iconal is a very powerful tool, and in fact, using the iconal approach and also some alternative approaches, people have been able to compute the classical part of the amplitude and the observables corresponding to 4 p.m., which are at precision of G to the 4. So these are the state-of-the-art computations in the post-Minkowskian theory. Okay, so these are equivalent to computing certain three-loop integrals, but the three-loop integrals, in fact, can be very easily solved using a novel technique, which basically it consists of IVP relations, which are differential equations for solving Feynman integrals. And you can use the post-Newtonian data, which is based in expanding at low velocities. You can use that as your initial condition, solve these differential equations, and get the full integral. Okay, so just to let you know that this has progressed and escalated a lot in the recent years. Okay, so that's the state of the art. And moreover, you can include radiation effects. These are related to the minor part of the amplitude, where there's some unshelled particles being exchanged. I'm not going to talk much about that in the interest of time. instead, let me just try to close because time is short. So let me just mention that there is a wave particle duality that enables us to go classically, but beyond the economic approximation. And this consists of the following. So we can consider perturbations of a black hole spacetime. Okay, and such perturbations, which if they are not symmetric, for instance, if they are non-spherical perturbations, they are very important because they are related to an open problem, which is the stability of the black hole. Okay, and this has been seen a lot of progress recently, in particular this paper for the Charles case. So we perturb our black hole by certain waves. So these waves can have helicity, they can be scalar waves or gravitational waves. They can have helicity 0, 1/2, 1, or 2. And Ray and Wheeler actually computed that in linearized at the linear level in the perturbation, but at the full nonlinear level in the black hole spacetime. Okay, and in order to describe the result, basically what they did was to take this quantity, which is a Newman-Penrose scalar, which I introduced in the beginning. You expand it in partial ways. You look at the radial component. So it's a separation of variable problem. So sorry, a separation of a partial differential equation. And the radial component of this Newman-Penrose scalar satisfies this equation. Okay, that's known as the Radial-Wheeler equation. Now, this Radial-Wheeler equation has a very similar form to the Schrodinger equation, which means basically that if you're going to compute scattering in this situation, in a black hole background, you can look at the Schrodinger equation and reinterpret the Schrodinger equation as a quantum field theory amplitude, where instead of putting this potential, you're going to put a particle. Okay, so instead of putting an effective potential, I'm going to consider a massive particle scattering with my wave. And
5 minutes.
Thank you. And I can compute the corresponding Newman-Penrose amplitude, okay, associated to this amplitude, to this quantum field theory amplitude, using the same formulas that I showed in the beginning. Okay. Now the crucial part here is that this doesn't require any economic limit, any consideration on the momentum terms. So the only thing we're assuming is that the energy of the wave is small. So in a sense, the wave is soft. It's small enough such that the long wave, the wavelength is longer than the Churchill radius. That means that basically we are seeing the black hole as a point-like object in this expansion. Okay, so under that assumption, we can compute this amplitude perturbatively and match it to the classical computation by Ray and Wheeler. Now, if we take this and further consider the economic limit, then we go back to our economic approximation, and you can check very easily that, or actually Ford and Wheeler did it, that this partial wave expansion becomes the economic approximation. And something nice that you find is that the economic approximation basically describes an effective action of a null geodesic. So that means that it doesn't matter whether you put a particle of helicity 0, 1, or 2 in this economic approximation. At the very end, you're only going to get a null geodesic in this approach, in these limits. So this is an instance of a wave particle duality. The simplest example of this was considered long time ago by Tooth, who considered a massless particle scattering with a wave or with a particle, and in such case it doesn't correspond to the Churchill background as in the Ray-Wheeler case, but it corresponds to a Chug wave background. Okay, so just to finalize with some final thoughts, which I probably don't have much time to explain, but I'll just mention that if we look at these 3-point amplitudes, basically they vanish because they have this delta function. Okay, so you might say, how are we going to recover, for instance, a black hole spacetime? But we know that the black hole information is contained because, sorry, let me just. We know that with the amplitudes that we have considered, we can just compute the two-body dynamics, right? So we can compute effective actions for two bodies. So in some way, these amplitudes contain the full information of the black hole spacetime. But the 3-point amplitude itself vanishes. So that poses a puzzle. And the solution of the puzzle, well, it has many solutions, but one solution is that actually these 3-point amplitudes vanish because basically there's no radiation of a single body. You have to consider more than one body, but they have supporting complexified moment. Okay, so that means they can be used as building blocks to construct these 4-point amplitudes from which we can read of all the information of the backgrounds as we want. So this is a standard law of the on-chip program. We're constructing higher point amplitudes by using lower point amplitudes in complexified momentum, okay, which are on-chip. And let me just mention, so this is the very last comment that I'm going to make, is that actually this whole program that I showed you can be repeated, except very few details, but most of it can be completely reproduced for the case of spinning black holes. So what changes is that instead of considering a scattering of a scalar massive particle, you're going to have to consider a scattering of a particle with a spin. So that spin maps to the classical spin of the Kerr black hole. And in order to reproduce the full information, you have to consider particles of infinite spin. Okay, so we completely nailed down a few years ago this 3-point object for the Kerr black hole. This 4-point object associated to gravitational perturbations of the Kerr background is still under study, but it provides a very important link between higher spin particles and black hole backgrounds. Okay, so this is all I wanted to say for today. Thank you so much.
Thanks. If there are questions, I think Nathan has a hand raised, and then Andy.
That was a very nice talk. I had the question, so for the post-Newtonian approximation, how does the theoretical error bar compare with the experimental error bar? Can you use your computations to check general relativity?
So it's negligible with respect to the SNR. So if you actually consider the signal to noise ratio, that makes it negligible. So in other words, we are currently, with our current measurements at LIGO, there's no need for more precision, as far as I know. But technology progresses, so we're expecting the Einstein telescope and LIS and so on. There is going to be a considerable error bar unless we include more corrections, more precision.
Okay, thanks.
Andy?
Yes, thank you for the beautiful talk, Alfredo. My understanding is that 15 or 20 years ago, the LIGO collaboration was very concerned that even if they detected gravitational waves, that the state of the art in understanding the relationship between the source and the waves was so poor that they wouldn't be able to know what they were seeing. And then there were these fantastic breakthroughs by Pretorius and Tucholsky and other people using variable computer meshes and advanced numerical analysis methods that brought in a whole new era of precision of source to wave matching, which relied heavily on technical advances in numerical analysis. Are you saying these methods supplant that, and we could now compare theory and experiment at LIGO just using analytic methods? Or because a black hole merger is an incredibly nonlinear thing, and it would be surprising if this kind of method could do that.
Yes, so there are different regimes, right? So numerical relativity, as developed by Pretorius in 2005 and other groups, is extremely powerful. Where at the very late stages of the spiral, it's not as powerful as you would think in the early stages of the spiral. So actually, there's some kind of syncretism between numerical relativity and analytic methods in the planche, which is the latest stage of the inspiral, where you have to combine the two templates in order to get the precision that you want. But let me just mention that there is another scenario where numerical relativity fails drastically, which is in the case of extreme mass ratio in spirals. So as you
so you're saying that no, these methods can't supplant the. There's still some things that we can't.
They're complementary. They are complementary. So if you consider a supermassive black hole, I'm not. My talk was not solely about gravitational waves. Of course, that's the most important application. But if you consider, for instance, a supermassive black hole with a very small body orbiting around it, then you cannot use numerical relativity because the size of the resolution is just not compatible with a small object orbiting a big one. So you have to use these analytic tools that we are currently developing. And in that regime, for instance, you would hope that such a computation can be done perturbatively to very high orders.
Thank you.
Gabriela?
Yes, thank you for the nice talk. I just have a small comment. While at the 3 p.m. level, I think the situation, the calculations are complete. At the 4 p.m. level, I think they are not yet. In fact, the calculation, which is based on conservative dynamics only, is still infrared divergent, and one has to add radiation reaction to it, and people haven't yet finished the calculation. And this is also important to have a unified description of the process from the deep non-relativistic limit all the way to the ultra-relativistic limit. So this, I think, has been done nicely at 3 p.m., but not yet at 4 p.m. 3 loops. Do you agree?
Yeah. Sorry. I was very schematical in that slide because, as you know, this is about a paper that appeared last week, and I agree with you that 4 p.m. is not complete. But my understanding is that they actually computed certain radiation effect at 4 p.m. Not only the conservative part.
We almost have it, Gabriele. We almost have the whole thing.
Almost.
Yeah.
That's what I wanted to say. I saw your paper. Of course, very nice.
We include all the radiation logs. All the radiation logs are there. All the nice logs are all taken care of.
Okay.
And the poles are all gone. And answering to Andy's question, actually, if you look at the waveforms, look at the neutron stars. The neutron star merge outside the band. You don't even need numerical relativity. It's purely post-Newtonian. So the waveforms I use for neutron stars right now don't even rely on numerical relativity. Without us, you couldn't do anything with neutron stars. Another thing about ET, going to 1 Hertz, you get tens of thousands of cycles with numerical GI will take you the age of the universe to run one simulation. So you actually merge everything together. And people here will insert the word effective OneBody, which is how you kind of stitch it together. But you rely on analytics to actually cover the majority of the spiral that has almost all the cycles. You rely on maybe, I don't know, 10, 20 towards the end, would you actually rely on numerical GR? Of course you need them, right? I mean, it's important to have them. But the majority of the cycles are analytic. And if we don't have, even up to, right now we're at 4 PN, 4 post-Newtonian and 4 post-Minkowskian. If we don't have 6 PN, we're gonna fail, even just, well, maybe not for detection. Well, it depends, maybe very eccentric orbits we might miss. But the parameters we're gonna get completely wrong with third generation detectors if we don't go higher orders from what we have right now. So actually it's very important.
Jorge?
Picking up on what Rafael said, I understand that you have to use the effective one-body approach when you want to connect the scattering to the bounded orbits. But I also understand that the effective one-body approach, as of yet, not been proved in its full glory. So do you think that there's a way of using these new scattering methods that you're talking about in QFT to help us prove the effective one-body approach?
Well, I'm not sure I actually mentioned effective one-body approach. It's true that this radial action is effective action for relative motion. So you can say it's actually one body or scattering with an object. So it's an effective action. It's true that the effective one-body approach was developed in post-Newtonian theory, and now it has evolved into post-Minkowskian theory. I'm not sure exactly what part of it is not proven, but what is true, and it can be derived from very general arguments, is that the Coulomb exponentiation happens in this low energy momentum transfer limit. So the Coulomb phase actually is not quite the radial action as you go to higher orders in G. So at first they coincide and they are exactly the same in linearized order. But as you go to higher orders in G, the Coulomb is slightly different than the radial action. So so far, I think that's the most reused method that we have.
But Alfredo, do you agree that this iconal or radial action approach, doesn't need to talk about the effective one-body problem?
Yes,
in fact, the effective one-body uses only the conservative part of the potential, which we know now is not enough.
They do add radiation reaction, Gabriele. They do it, but they do it by hand. Yeah.
Yeah, that's right. So, I think it's better to use the radial action or the iconal, because if you do it well, you pick everything.
Yes.
Yes.
Can I ask you a question
from Andy? We are
running
out of time, so maybe one more question from Andy.
Yes, I had another question. So you had a slide with the phrase black hole is an elementary particle. Now, of course, a black hole is the opposite of an elementary particle because it has exponentially many degrees of freedom, but it might, in some circumstances where you're discussing it, be behaving like an elementary particle. So my question is, does this formalism have within it some way which you might be able to think about, treating black holes in their full glory with their many microstates?
Okay, so that's why there is a classical prefix to the title. But I know. So actually, in effective field theory, how this scene started in the 90s is that people wanted to compute corrections, quantum corrections to Churchill or the Kerr metrics. And in effective field theory, there is a natural way of incorporating corrections in H bar, but it's still linearized. It's still linearized gravity. So it's up to debate whether you can measure any effect at this in this framework. So it's a perturbative framework. I'm not sure if you can actually compute something observable.
There's one more question from Juan, and then we'll move to the next
my question was related to the previous one. So the black hole can deform, right? And at some order, the deformation of the black hole will be important. As I understand, this can be taken into account in this effective field theory approach. I was just wondering whether this effect, and on the other hand, it seems that from this other scattering amplitude approach, you could, at least naively, I would say you could not take such an effect into account. Am I wrong? Or
so you mean tidal deformations?
Yeah.
Yeah. So tidal they can completely be incorporated. These are just non-minimal couplings in the scattering amplitude.
Okay.
Okay. I think it's time to
make one comment. It seems like this is all working much better than it has any right to. And so one wonders how far one can go with it.
Yeah.
Well, that's a standard law in scattering amplitudes. Things work much better than they are supposed to until we actually understand what's the underlying construction.
Nobody knows, I guess. Okay, let's thank Alfredo again for this nice talk, and thanks for the nice discussion. Mariano, maybe you can start sharing your screen.
Yes.
There's a question on the chat. I'll let the people who are in the field answer it, and you can have the discussion on the chat, and you can answer it on the chat. Our next speaker is